Hi everyone. Today we're going to talk about visual analysis of networks. But I want to start us off with the discussion of information visualization in general. Information visualization is a way to show lots of data visually to help people with analysis. And this works because as humans, our brains are configured to recognize patterns in visual information. So if we're able to show data in a visual way, we can take advantage of some of our natural skills to pick up on patterns. In general, information visualization is geared towards helping us find what's interesting in the data. So that means identifying trends or clusters or patterns, but also outliers or anomalies. And information visualization is used both to communicate information, so information graphics, infographics are one example of this, but also to discover and explore the data. So we're going to look at some Info Vis in general, and then we'll move on to talk about graph visualization or network visualization specifically. So this is an example that when I started teaching, all my students remembered, and now it's kind of hit or miss. But the Challenger was a space shuttle that was launched in 1986, and it exploded on launch, and it was a big deal. Lots of kids were watching because there was an elementary school teacher who had trained as one of the astronauts who was going up, so it was like a school activity for everyone to watch the launch. If you remember this, you don't need to watch the video. If you don't remember it, you might want to check out the video here just so you can kind of see what happens. You can see in these stills that the shuttle's taking off, but there's something here that shouldn't be happening, and a little bit bigger here, and then the explosion is starting here. So there was a big investigation after the Challenger exploded that went on and on to try to figure out what actually had caused the explosion, and it turns out that what it was were these things called O-rings. And again, if you were around at this time, you remember constant talk on the news about O-rings. And you can sort of see them here. You can see that there's a circle going around. O-rings were these basically rubber gaskets that fit in these sections of the rockets here. Those failed, and that caused a fuel leak, which then ignited and caused the explosion. Now, this is something that happened not infrequently. There was often damage to these O-rings, but that damage wasn't necessarily a reason that the shuttle couldn't launch. So engineers would often take a look at those O-rings, the kind of damage that they would find, and correlate that with other data. This is the visualization that they had at the time of Challenger's launch about damage to the O-rings based on weather. And this is important because the weather was very, very cold on the day of the Challenger launch. So what we're looking at here is the two rocket boosters, A and B, and then the shuttle mission underneath. So this is shuttle mission 1, and we have rockets A and B. Here's mission 2, rockets A and B. On the first rocket for each launch is the temperature of the launch, and then there's different markings indicating the severity and type of damage on the O-rings. So you can see we don't have any damage here, there's some here, and so on. So the question for you is, what is actually going on? If we're looking at the time of launch for the Challenger, where temperature is near freezing, should we launch or not? Is there a correlation between temperature and damage? Does the damage get worse when it's colder? What can you see from this? And you have to make a quick decision. So I'm going to be asking you a lot of questions like this in the lecture, and I'd suggest you actually pause the lecture for a second and stop and jot down a couple notes on a piece of paper for yourself, because it'll help you just remember what you actually were thinking. You'll be able to see some of these patterns and some you won't. So pause it here and write down what you think is the relationship between temperature and damage. Honestly, it's pretty hard to see from this because sure, we have some damage on this one cold day where it's 53, but we also have a bunch of damage here when it's 75. If we plot this information in a different way, here we have the damage index. So higher is more damage. And here we have the temperature in Fahrenheit. So you can see all of our data is clustered up here, and way down here is the temperature that was forecast on the day of the launch of the Challenger. So we can maybe see some patterns here, but then if we fit a line to this, this is what we see. So as the temperature gets colder, we get a really dramatic increase in the amount of damage to the O-rings. How would this trend continue if we follow it all the way down to the temperature down here? Looking at the data this way, it makes it really clear that there was going to probably be some serious damage to those O-rings because the temperature was so cold. But seeing this kind of pattern in data visualized like this is really hard. And this is a classic example of information visualization used to say that while we can come up with fancy ways of displaying things, you want to think about what's the task that people are trying to do. In this case, they're trying to forecast the type of damage that we might expect based on the temperature. And a plot like this is much more effective at communicating that kind of information than what we saw when you have the graphics of each rocket. So the main idea of information visualization is that visuals help us think. They provide a frame of reference. Based on cognitive science, we have a temporary storage area where we can process visual information that's different than the way that we process information in text or other forms. And it helps with external cognition. So this is the role of the external world in thinking and reason. So let's talk a little bit more about information visualization just in terms of definition. What is information? Well, in this case, we're talking about items, entities, or things that don't have a direct physical correspondence. So this could be things like baseball statistics, stock trends, connections between criminals in a criminal network, car attributes, and so on. This is contrasted with scientific visualization, which is also a way of visualizing data, but it generally relates to things that are physical or geometric. So if you are looking at, say, liquid flowing through a system, and you're actually looking at the flows of that liquid, that would be a scientific visualization. There's a direct correspondence between the data and some physical property. So examples listed here: an airflow over a wing, stresses on a glider where you can actually look at the glider and see the stresses, or weather visualizations where you're looking at a weather map. That is information that you're visualizing, but we tend to group those as scientific visualization as opposed to information visualization. Key attributes of information visualization. Scale is an important issue. If your data gets really big, then it becomes hard to visualize it. There's only a fixed number of pixels on the screen, and so even if you were to make a super dense visualization where each pixel represents one piece of data, you still are going to run out of space with a relatively small data set. So we have to think of creative ways to scale our visualizations. Interactivity can also be important, where there we want to show multiple perspectives on the data, allow people to change their views, change what they're looking at. And what's really important, and this is true for information visualization, but also human-computer interaction in general, is to think about tasks. So task is a specific action that a person wants to carry out. So we want to think about what are the things that people want to do with the visualization we're creating. It's really easy to create something that looks cool in information visualization. And this is a real problem because there's lots of people creating cool visualizations that aren't necessarily useful. So you want to think about, what do we want people to do with this visualization that would be hard to do without it? And this helps us support discovery, decision making, and explanation. So here are some tasks that are common for information visualization. One is for search, and there you're looking to find a specific piece of information. So how many games did the Cubs win in 1995, or what novels did Ian Fleming author? Another common task is browsing, where you want to look over the data in a more casual way to see things that are just interesting and you don't know what those are ahead of time. So in a network, that could be looking for clusters, for cliques, for tight little groups, or for nodes that really seem to be disconnected from the main part of the network. For analysis, we'll often do things like comparison and differences, say between networks or between groups of data. Look for outliers or extremes or patterns. We'll also do some of these other tasks: assimilation, monitoring, and awareness, which is looking at how the data fits in with other things that we know. So how does information visualization amplify our cognition, help us understand better? Part of this is cognitive, and it's based on cognitive science, how the brain works. Using visualization increases memory and processing resources available. Separate parts of our brain are used for processing visual information as opposed to processing other information. So if we can offload some of our cognition and cognitive tasks into the visual space, it helps us think more and process more in the other part of our memory because we have some of that processing happening visually. It helps us reduce the search for information. We can look at particular parts of the data and ignore others. So if we think back to that graph of the O-ring damage based on temperature, we're not really interested in the damage that happened around 80 degrees. We're interested in the damage that happened when it was really cold. So instead of looking at every single data point like we might in a chart, or that we were looking at when we had the visualization with the pictures of the rockets themselves, we can look at the trend overall, which is really one piece of data, and then the point where we want to see where that trend intersects. So we don't have to look at all the data, and it reduces the search that we have to go through. Visually, we're able to recognize patterns quite easily, so visualizations help with that. They enable perceptual inference operations. So these are natural skills that we have to identify outliers. A common example we use when introducing information visualization is to show you a slide that has a regular pattern of squares, and one of those is replaced with a circle. It's actually quite easy to pick that out. So we can make inferences that way. Similarly, if we have, say, a chart, it's common that we can fit a line to that. So even without drawing a line on it, our brain can recognize patterns in data. We can use perceptual attention mechanisms for monitoring. So if you're looking, say, at a weather map, you'll notice when part of a storm turns red. So there we can monitor the data and we'll see changes that appear. And we can encode information in a manipulable medium, which means we can take this data and instead of just showing it as text or a chart, we can put it and display it in a way that people can manipulate it. They can show it in different ways, they can change the views, and you'll start to get used to doing this with network information in the tools that we're going to learn in class. So network visualization is what we'll be doing. Here we want to visualize network data, so nodes and edges and potentially attributes of those. But when we're doing network visualization, we want to keep in mind the principles for information visualization in general. We're trying to find patterns, we're trying to support tasks, we're going to help people search and browse the data, and we're going to look for patterns or outliers. So before we move on to this network, I want to show you some example networks, and we can discuss if they're good or bad or neutral visualizations. These are linked for you in the notes. This first tool is called the Visual Thesaurus. It's a thesaurus, and we can put in a word, so let's put in network. Look it up, and what we get is a visualization here of the word and its synonyms. And those synonyms are grouped together if they have a similar meaning. So here we have network related to intercommunicate and communicate, so there you're networking. Here we have net, meshwork, meshing and mesh, a certain kind of network. Here we have communication terms, and then a few network types here. So this looks pretty cool, and we can click on a term. So here I'll click on web, and then it redraws this network for us with synonyms for web. Okay, so this is pretty cool. It moves a little bit, and that's kind of awesome looking. But what's the really useful thing about this visualization? So this is another part where I want you to pause this and think about what we talked about as tasks for visualization. What are we trying to support? We're trying to support things like search, browsing, finding patterns in the data, finding outliers. So pause the presentation now and write down for yourself what sorts of things the visual thesaurus is useful for in terms of the way we evaluate information visualization. Okay, so hopefully you didn't cheat and you wrote something down. If we come back, I'm going to argue that this really isn't useful as a visualization in terms of the way we evaluate information visualization that I presented in the slides. Yes, we're able to see the synonyms of the word in the center, but we could easily see that in a text list. We could have the word listed and all the synonyms below that. We could also have the synonyms grouped. So if you imagine typing this into a Word document, you could have your main word as the title, and then each group of synonyms together with a blank line in between separate groups. You could make that interactive, where you could have a web page that displays like that, and you could click on a word, and once you click on that, instead of getting a new visualization, you simply get a new page with a new list. So this visualization isn't communicating any information visually that we couldn't find in a list. That's important because even though this looks cool and it can be engaging and it may make people want to learn more about words, for information visualization, we're not talking about engagement or attention holding. We're talking about the specific information seeking tasks that we're trying to support in people. And this really doesn't support anything new. So that's not to say that this is a bad tool or that it shouldn't exist. There's lots of reasons that this can be useful and helpful. But if we talk simply as an information visualization, this isn't communicating any information that we couldn't see as easily and as effectively in a list. So there's example 1. For our second example, we're going to look at this static visualization. This is the Egypt Influence Network. So this is looking at tweets in Egypt during the revolution there. What we have is a network, so it's zoomed out right now, so get a look at the whole thing. I'll zoom in. And so here you can see each node is a Twitter user, and there's connections indicating influence between the nodes. That influence here, as we can see, is just if users follow each other. So we have following relationships here. So here, this user, you can kind of see all of the edges that are connecting him to his friends. So we have a very dense network of people who are connected here. And we have people who are tweeting in English in blue, who are tweeting in Arabic in red, and you can see we have some purple nodes if we zoom in here. And those people are tweeting in both languages. The bluer it is, the more English, the redder it is, the more Arabic. So what can we see from this data? In this case, the individual nodes don't really matter, but what we are interested in is the patterns that appear. So by color coding these nodes by language, we can see a bunch of really interesting things. First is that you tend to have English speakers linked together and Arabic speakers linked together. On the border between those two groups is where we find a lot of these purple nodes that are tweeting in both languages. And there are some outliers. So for example, here is a blue node connected to a lot of these nodes that are tweeting mostly in Arabic. So we have an English speaker enmeshed in the Arabic network. Similarly, down here we have a lot of people who are tweeting in Arabic, but that are mostly connected to nodes that are tweeting in English. So these could be, say, members of the media who speak in this case, who speak in Arabic, who are embedded in Egypt, but who are tweeting in English for their audience. The same can be true down here. These also may be Egyptians who are in an English-speaking country, so they're mostly connected to English speakers, but who are tweeting about the Egyptian revolution in their native language. So this really illustrates a lot of the things that we can do with information visualization. It's not as fancy as the visual thesaurus. It's not moving, it doesn't spring around, it's a static visualization, but we can see some really clear patterns in the language. So we get large patterns, a group of Arabic speakers, a group of English speakers. We can find outliers, people who are speaking one language even though they're enmeshed in a network of people who are speaking something else. This really is a great example of being able to visually discover information, where if you had this in text, it would be hard to look at a list of nodes the language that they speak and the people they're connected to, and discover that. So this is the kind of visualization that you should be very happy if you're able to make as we go through this in class. So let's switch back to our slides and go through some examples so we can start thinking about visual analysis in networks. We have a much simpler network here. We have a bunch of nodes. And again, this is a point where I want you to pause the lecture and write down for me 5 things that you are spotting as interesting in this network. There's no right answers, there's no wrong answers, and while I encourage you to share this with other people in the class, it's not necessary. Okay, so hopefully you wrote some things down. Some things that I find interesting. This node A here in the middle has a lot of connections. If you remember back, we can call A a hub. It has a lot of connections. Here we have a really tightly clustered group. We don't know that it's a clique. It's probably not a clique. There's probably some edges missing there, but we have a really well-connected group, and that's interesting. So there's something going on with these nodes down here. All of these nodes surrounding A don't have any other connections. The only way they're connected in this network is through their connection to A. And that's even more dramatic here, where we have B, another one of those nodes connected to A, but then this long chain of individuals who are just connected to one another. So B4 is really far from everybody else in the network and only has this one path to get to the rest of the network. Now, we haven't learned that much about networks yet, and you certainly haven't learned anything about how to apply visualization techniques to study them, but hopefully you picked out some of those patterns as you were jotting down things about this network as you paused it. So those are some things that you can pull out just through a simple visualization. What makes a good visualization? This is a list that Cody Dunn and Ben Schneiderman came up with. They're information visualization researchers based here at the University of Maryland, and they wrote a paper on this. They said good visualizations, every node is visible. For every node you can count its degree so you can see all of the edges coming out of a node. For every link you can follow it from source to destination so you can see every connection. And clusters and outliers are identifiable. Now we can't always do all of this, but it's a good rule of thumb to start with as you're thinking about it. Now if we switch back here as a counterexample, in this Egypt network, we definitely can see all the nodes, but we can't count the degree of every node. If we zoom in again, what's the degree of this node? We can't even tell which edges are connected to it. We can't follow those edges from start to end. We may be able to identify an occasional edge, but most of them are overlapping. There's just a mess of edges here. And so we're violating a lot of the rules of what makes a good visualization, but this visualization is still great. It's just achieving a different purpose than those rules were designed to think about. So these aren't hard and fast rules that these things must be true all the time, but they're good rules to follow, especially when you're making smaller visualizations. So let's start and think about a network and try to apply some of those rules. Is this a good visualization? Write down for yourself if you think so. My answer is going to be no. We can't really identify anything interesting in this network. We can't see which nodes have a high degree or a low degree, how they're connected, what the patterns are. We just really can't discern very much. The things we can pick out, there's some nodes here on the edge that only have one connection. We can see their one edge going in. We can see that this node down here probably has a lot of connections, but that's pretty much all we're seeing. What about this network? This is an interesting question. There are certainly things that we can discover from this. We can see that A has a very high degree. It's connected to a lot of nodes here that have a low degree. We can see here we have a bunch of nodes that are connected only in a chain, and then a lot of nodes here that are connected to one another. So hopefully at this point you've recognized that the network we're visualizing here is the same one that we started with, but we're looking at it in different ways. This is called a ring or a circle visualization, and it can be really useful. Lots of people use this. Now there's certain patterns that don't emerge very well here. For example, we have a tight cluster here, and we know that from the first visualization, but it's not quite as apparent here. We can see that there's this collection of edges grouped here, but it doesn't stand out as well as it did before. So this is a good visualization, but probably not as good as we can do for conveying information about the structure of the network. What about this? This uses a grid layout, so each node shows up in a place and they're aligned in a grid. We can see that A has a high degree. We can see that most of these nodes down here have a low degree. We can see the path connecting B3 back to A. And we can see that there's a lot of connections between our nodes here that form that tight cluster. So again, not a bad visualization, but maybe not as effective as the first one. And now here we're back to a similar layout to what we had in that first network. This is called a spring-embedded graph layout. We'll talk more about those types of layouts. But again, we can see A has a high degree, all of these nodes surrounding it have a low degree, this long path here, and the tight cluster of nodes over here. I think this is probably the most useful visualization, and in fact this type of visualization, this spring-embedded or force-directed graph layout, is the most common that you'll see when people are showing visualizations of networks. There are other things that we can vary. So here we have the same network, but we've changed the size and color of some nodes. You can set the size and color to represent different properties. So if we switch over for a real-world example here, we have nodes of different size. That's representing the influence of the nodes. And remember that influence is if people have a following relationship. So nodes that have a lot of followers are going to have a higher degree. So we can see that here are some big nodes, but there's also a lot of little nodes that have a lower degree. Here we've encoded the color to represent language. So we've encoded size and color to represent different things, and that lets us pick out more information from the network. Here, we're not specifying what size and color represent, but we can clearly see a large size over here, and we can see the color here. So if you want to write down for yourself, what do you think the size and color represents in this network? Okay, so again, hopefully you didn't cheat and you wrote it down. In this case, the size is representing the density of the node's neighbors. So because we have a tight cluster here, each of these nodes is connected to most of these other nodes here, and they're mostly connected to one another. So the density of each node's immediate network, their egocentric network, is quite high. Thus they're bigger. These nodes out here, mostly none of their friends are friends with one another, so they have a very low density, often a density of 0, of their egocentric network, and so they're smaller. So size is representing density of the egocentric network. Color is representing degree. So our darkest node is this one in the center, which has been node A. These nodes also are all connected to each other, so they have a relatively high degree, but most of these nodes have only one connection, and so they're really light. So we're representing density with size, degree with color, and then we have the same layout that we had before, so there's a lot of information that we're able to convey here. Here's another network. We've represented size and color here. In this case, size is representing betweenness of the nodes, which we've talked about before, and color is representing clusters that were automatically detected. The clustering is interesting. This is something that's done automatically. We're not going to go too much in depth in class into how clustering actually works. It's a pretty complex process, but I'll include some pointers to you so you can see how it works. But it's an automated technique, and it identifies nodes that kind of belong together in one sense or another. And that makes it easy to pick out groups here. So we have a yellow group here, we have a red one in the middle, there's a purplish group up here, a blue one down here, and a green one over here. There's certainly some nodes that mix around, and that's normal, but that clustering allows us to identify some clear patterns, and we can see the most influential nodes are a little bit bigger, and they tend to be along this path here. As we mentioned in the very first lecture, edge weight can also be represented, and for edge weight we tend to do edge thickness. So we can see here we have some highly weighted edges along this path, some medium weighted edges here coming out of node A, that important one in the center, and then not very high weights among the edges up here. Okay, so just to talk about some issues that come up when doing this visualization, scale is really important. It's common that we have large networks, and when we get too many nodes, which tends to be around 10,000, it's almost impossible to visualize a network. The same is true if we have a lot of edges. You can put it into a tool and it'll produce something, but the visualization that you end up with generally isn't very useful. It's very hard to see patterns in that. So super dense networks or really big networks, it's hard to see patterns in them. Now that's not always true. We had a very big network on the Egypt example that we've been looking at, but it's not that big. We don't have 20,000 nodes in there. We have a much smaller number. So you will definitely run into issues where you have too many nodes or edges to visualize well. And in that case, we'll apply some filtering or some ways to group things together so we can start to see some patterns. Here's an example. This is a network of all the members of the Senate and their voting records. So each node represents a senator, and each edge connects senators who voted together on at least one bill. So what we basically have here is a giant clique, because there's bills that everybody votes on the same way. So there's not a lot of useful information that comes out of this. One, everybody's voted together, and two, we can't see anything about edges in this network. We just kind of have this blob. Sometimes it's called a bunch of spaghetti. There's nothing that we can see. But if we apply some filtering, so we filter out edges based on weight. What that means in this case is we filter out edges based on how many times senators have voted together. What ends up happening is that we get two groups that tend to separate. These happen to be Republicans. These are Democrats. So we're looking at only the nodes that represent very high voting similarity here. And then we've got some senators in the middle who tend to be these bipartisan people who are looking at making deals. And I'll provide you a link to look more in depth at this particular visualization, done in a nicer way, that highlights the separation of senators based on their voting records. So this is a place where looking at the network alone, it's far too dense, we can't see anything, but if we filter properly, we can see some really interesting patterns emerge. These are the examples that we talked about before, so you have them linked. And what you're going to do next is try out some visualization tools. There's two main ones to look at. Gephi is the one we're really going to focus on in class. It works on all platforms. It's a standalone program that runs with Java. It's open source. It's a little bit buggy on occasion, which is kind of its downfall, but that's something that happens with most with most open source platforms. The other option is NodeXL. This is also open source, so it also has some bugs. It works on Windows only. It's free, but it's a plugin for Microsoft Excel, so you have to have the right version of Excel running on Windows in order for NodeXL to work. It has some features that Gephi doesn't, which are really useful, particularly ways of importing data. So I'll show you a couple examples of that. My recommendation is that everybody installs Gephi. All the examples I do for you will be using Gephi. And if you have Windows, or if you have, say, Parallels on your Mac or access to Windows machine, that you also install NodeXL. I kind of use them in a couple ways. I mostly use Gephi myself, but sometimes I'll go to NodeXL to import some data, and then I can either use that data directly in NodeXL or copy it over and use it in Gephi. Both are really good tools. They'll work well for you in class. And as you explore them, you'll find out there's all sorts of interesting things you can do with them. So I'm going to have you guys go try out a tutorial on Gephi. So I want you to do that first, or if you really are committed to NodeXL, you can do it there. And then I want you to do this in-class exercise. load the assigned data set in NodeXL or Gephi. This is going to be linked on the main web page for this lecture. And then create a visualization for me using color, size of nodes, layout, and other features to tell some story or to provide an insight into the data. So you can do whatever you want. You can use whatever layout you want. You can make size and color match whatever feature you want. But get some insight based on the visualization that you create. And then I'm going to have you upload this to our discussion space, and that will allow you to discuss and share your insights with other people.